Okay, let's get started. So today we're going to switch gears. We're going to start our coverage of MRI for this course. Before we get started, are there any questions about course logistics? I think everyone knows I guess you're working on your project once. And then there'll be some additional instructions coming out, I think, later today, right? We'll want everyone to put your things on a YouTube link just so that it facilitates other people looking at your videos and asking questions. All right. So are there any other questions before we get started? Okay, if not, let's get started. So today we're going to cover these topics, most of them at least. We're going to talk about what an MRI system looks like, and then we'll talk about spin and magnetization and probably get through precession RF excitation. Okay, so this is basically what an MRI scanner looks like. So it is the most common geometry is it's like a bore, a horizontal bore, although we'll see other geometries. And you essentially put the patient in the bore. So looks very much like a CT machine. And the main thing with MRI is instead of having X-ray detectors, we're going to have three different coils. And so we're going to spend a lot of time talking about what those coils are, right? The biggest coil is this coil here. It's the coil that creates this huge magnetic field, okay? And that's the biggest coil. Then there's the radio frequency coil that's labeled there, and then there's also the gradient coils. So there's the magnet, the radio frequency coil, and the gradient coils. So those are the three things we need to understand why they're there and what they do. So we'll start off with the magnet coil, which is basically made up of wound wires. So it's a solenoid coil. So it creates a uniform magnetic field inside. But typically, since we want really strong magnetic fields, these are special coils in the sense that we need to use superconducting wire. So that's expensive. And we need to keep those wires cool. So we need liquid helium. And so these magnets essentially are huge because they essentially have a lot of wire and they have a lot of liquid helium to keep the wires cool. Okay. So let's talk a little bit about magnetic units. So we're going to use two sets of units in this course those are used in the MRI field. Tesla is one. Does anyone know? Like, it's not named after the car company, so it's named after Nikolai Tesla, who was a famous inventor in the late 1800s, early 1900s. And so it's named after Tesla. And so when we're talking about the strength of a magnet, we'll typically use Tesla because it's typically on that order. For example, the systems I use typically are like 3 Tesla magnet. Okay, so it's very common. So 1 Tesla equals 10,000 Gauss. All right. Uh, and so just as a sort of good thing to keep in mind, the Earth's field is about half a Gauss. So sitting right here in San Diego, if you look at this map here, we're sort of right here, right? You can see we're right about 50,000 microtesla or half a Gauss. Okay, so that's the strength of the field. So if you think about that, if you go from half a Gauss to 1 Tesla, that's 20,000 times the Earth's magnetic field. All right. If you talk about 3 Tesla, that's 60,000 times Earth's magnetic field. So we're talking about fields that are much, much stronger than the Earth's magnetic field. These are some examples. So this is a scanner we just got. We just booted up last month. It's not blue, it's just lights. We can make it have different colors. So not all magnets are blue, but this one they decide you can have 6 different colors for your magnet. So you can turn on the colors depending on what the patient wants to see. So that's a 3 Tesla magnet, which is a pretty common magnet for sort of like academic medical centers. So here at UCSD, we probably have like 7 or 8 of these 3 Tesla magnets. Okay. Now, if you go out into sort of the community, you might have a 1.5 Tesla magnet. So you may not necessarily have a 3 Tesla magnet. So 3 Tesla, say 10 or 20 years ago, was considered high field. The next level up is 7 Tesla, although there are 5 Teslas, but 7 Tesla is the next most popular magnet. There's probably about 100 to 200 of those in the world. So those are mostly at research sites. So they are approved for clinical use, but it's very rare to see them used clinically. So if you go to UCSD, for example, you'll probably be scanned on a 3 Tesla magnet, right? And then there's a few of these really high field magnets. There's a 9.4 at Chicago, a 10.5 in Minnesota, 11.7. I don't think it's working at NIH. It's certainly not working now with the shutdown. And then 11.7 in France. All right. So we'll talk a little about why people keep building such big magnets. This is just showing you, this is 2019, there were 170 systems. And just to show you that there aren't that many of them, whereas, right now there's probably, in 2015, there's 850 3Ts. It's probably, maybe a couple thousand now. So that's typically the 3 Tesla is much more prevalent. This is one of the reasons why people don't really build too many 11.7 Ts. If you look at the size of this magnet, you see this person here, right? And this is the magnet. Okay. So this is a huge magnet. All right. And they've spent 20 years building, probably 10 or 20 years building this magnet. So far, they've only got a few images off of it. It's very, very expensive to build this, and it's very hard to get it to work. The hope is that, as we'll see, the bigger magnet you build, the more information you can get, but it's just a very hard thing to do. Okay. Um, this is just showing that, for example, how much stored energy this has. So the way these magnets work is when they get installed, they're not at field, and you essentially plug it into the wall and you start running current through it and you build up the field. So you're storing a lot of energy in the magnetic coil itself. And so this one stores 338 megajoules of energy. So basically the equivalent of, a few gallons of gasoline. Okay. So, but it's all stored there. So it's as if it's enough energy. If you took a few gallons of gasoline and lit it on fire, that's how much energy you have. Okay. This is just showing like that there are a bunch of high field magnets being built at different places. And let's talk a little bit about what magnets look like. And so what you're seeing here is this is a magnet that is letting off liquid helium. Okay. So in general, that would be bad. Okay. Because basically that's what's called a quench. And it's basically you let off the liquid helium, the wire is going to heat up, you're going to lose your magnetic field. Okay. So there's only one time you should quench a magnet is when you want to bring the field down to move it. Okay. The other time you quench a magnet is if someone gets stuck in the magnet and it's a life endangering situation, then there's a button you can press. But you should never press that button unless you are sure, because it's very expensive to quench a magnet. You're talking about $50 to $100,000 decision if you press that button. Okay. If someone's dying, obviously you press the button. But if it's just you have, like one time we had like a spool of wire that got stuck in the magnet because someone forgot. And I'll show you some examples of why you should never do that. But there, we did not quench the magnet. Instead, we tied a lot of ropes to that coil, and we had a bunch of people slowly pull it out. And luckily, we were able to do that. Okay. And then the other time is sometimes magnets just quench for some unknown reason, like maybe some ice builds up or there's something problem in it, and it just spontaneously quenches. And that's also bad because if a magnet quenches in an uncontrolled fashion, it may not be possible to bring it back up the field. Okay. And unfortunately, like we had a magnet where it quenched. We don't really know why. We think there were some problems with the system. And then we had to make a decision. Do we roll the dice and spend $100,000 to ramp the magnet up, knowing that it may not come back up the field, or do we buy a new magnet for $1 million? So these are the sort of decisions you have to make when you're dealing MRI. So it's an expensive thing to deal with. This is sort of example of the liquid helium let's see, where is this? Liquid helium dewar. And then on the side of the magnet, there's a lot of electronics. So underneath the hood, there's a lot of electronics that goes on. And then once the hood is placed on, it looks really nice and clean. So this is another Siemens magnet that we have, which once it's all installed and everything, you don't see all that electronics. Okay. So typically there's electronics on the magnet, and then there's a whole nother room with even more electronics. Okay, so let's talk a little bit about what can go wrong with MRI. Okay, so you have this really, really strong magnetic field. Okay. So if you were to bring one of these chairs, I assume these are some metal in them, within a few feet of the magnet, it would be ripped out of your hands. And as you can sort of see, it can pull those like beds into the magnet. Okay. And so one of the main things is that you need to be really careful when you're around a magnet. So if you remember nothing else from this part of the course, just remember the magnet is super dangerous. And the other thing is it's always on. Okay. It's not like at the end of the day we turn it off. Now, in the future, there might be things like that. But for now, you should assume if you are like, even if you're getting in a hospital or an outpatient facility getting an MRI done and you see someone do something like bring something into the room and you're going to get an MRI, you should feel free to just say, well, are you sure you can bring that in? I was just on a call yesterday where there was another incident that happened at one of our facilities where someone at midnight brought something in and it was pulled into the magnet. Okay. So large things can be pulled into the magnet. And if there's someone in the magnet, that person is likely going to get killed. Okay. So that's one thing. So for example, the most common thing of death is oxygen cylinders being brought in and just flying into the magnet. Okay. And then every year before I give this lecture, I see what has happened the past year. And so, for example, well, this was 2 years ago. So there was a nurse that was crushed when this thing was pulled into the magnet. And then the most recent thing was this in New York. There was a guy wearing a heavy iron necklace around, like a weightlifting necklace around him to like carry weight and build up his muscles. And he went in to see how his wife was doing, and he was like pulled into the magnet. Okay, so literally just dragged him into the magnet, and he died. And then this picture over here is a chair being pulled into one of the magnets here at UCSD. And that magnet is now dead. Okay. And it's very expensive when a magnet goes down because to take a magnet out of like a hospital, you've got to break down all these walls. So you essentially have a very expensive paperweight because it might cost you $1 million to get it out. Okay. So that's sort of my spiel. This is a really good video to watch. It's about 10 or 15 minutes long. So it's sort of fun to watch. So you can watch this. And I'm not sure there's questions about that in the homework, but there's a link there. As I said before, the most important thing to remember is the magnet is always on. Okay. Now, typically the magnet seems like it makes a sound. You'll hear like this chirping sound. If you ever go into a magnet room, you'll ch 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 ch. That's just the helium pump. Okay. Now you can turn that helium pump off, but the magnet's still on. So if you're ever working around magnets as part of, some research you're doing, just realize that even if there's no sound around the magnet, that field is probably on. You should assume it's on unless someone tells you, oh, I turned it off. Okay. Okay, so let's do our first sort of in-class exercise. And so we're going to do a little thought experiment here, okay? So imagine you're doing MRI research for your master's or PhD, and you walk into the magnet room, okay? And you forgot about this lecture. So you're carrying like a wrench, an iron wrench, okay? And you're like walking towards the magnet, okay? And at point A, the wrench gets ripped out of your hands. Okay, none of you are strong enough to hold a wrench close to a magnet. There will be hundreds of pounds of force exerted at some point, and at some point, thousands of pounds of force. So at 100 pounds of force, most of you will let go, right? They'll just be ripped out of your hands. Okay. So now the question is, and let's say it gets ripped out of your hands right here at point A. So I want you to think for a little bit, what's going to happen next? In the next less than a second, what's going to happen? Where's that wrench going to go? Where is it going to end up? So feel free to think about it, talk to your neighbors or whatever. If you're online, you guys can chat with each other. So I'll give you guys about a minute and a half to sort of think about this, and then we're going to regroup and see what people think is going to happen. All right? Okay, let's sort of see where people are. So the magnet at A, it's right at the center of the bore. So where do you think the magnet's going to go next? Okay, it's going to go to E, right? So if you think about potential energy, it's going to go sort of like it's going to go this point of potential energy to another point of potential energy, right? Okay, so it goes to E. Where does it go next? If you're very unlucky, where does it go back after it hits E? It goes back to A. Okay. It's going to happen before you even know it. So the moment you actually even realize it's being pulled out, it's going to be flying right back at you. Now, if you're very lucky, it's going to hit the side of the magnet bore and bounce around, and it may not come back and hit you directly. Okay. But if you're very unlucky, it's going to go straight through the magnet and then come back. Okay. So this has actually happened to people I've talked to, and luckily they didn't lose their finger, they just got nicked. But it is something that if you're working around a magnet, just remember, first of all, if someone was in the magnet, you would have killed them. Okay, because it would like typically, it would just if it hit their head or any part of their body, it would have just gone right through their body or done great damage. Um, and even if there's no one in the magnet and there was nothing in the path of that wrench, you would be the one to sort of suffer the consequences. All right. So hopefully I've scared you enough. So that's the scaring part of the lecture, right? Okay, so the other thing that is sort of a safety concern with magnets, but a little less so these days, is the fact that, like, if I had a magnet in this room, the magnetic field would be strongest in the magnet, but it was also sort of, as you know from like physics, you have a solenoidal coil, the field goes around the coil, right? And so those are called fringe fields. And so we have to worry about that because if I had a magnet here and someone was walking through the hallway, they would be also walking through a magnetic field. Okay. So where might that be an issue? Like, why would it be a problem? Like, let someone running down the hall, like what sort of person would have a problem running down the hall and there's a magnetic field? Can you think? Pacemaker? Someone with a pacemaker, exactly, right. So because remember from freshman physics or whenever you took physics, E is proportional to dB dt, right? So if you've got a field and you're running through it, you're changing the field with time, right? And then that's going to cause electric currents, electric field in you, and that could cause the pacemaker to go off. So typically, what we're showing you here in red is that's the main windings, and typically we'll have opposite windings to try to reduce that fringe field. All right. But even so, whenever we install a new magnet, we need to sort of understand what do the fringe fields look like. So here we're showing that um, the fields are really strong here at the center of the magnet. Whoops. At the center of the magnet, we're at 3 Tesla, I think, or what is this? 30,000 Gauss. Yeah, 3 Tesla. And then, or that's probably 1.5 Tesla. And out here, we're at we try to be at the half Gauss line. So that's considered the safe zone traditionally, that you want to keep the half Gauss line or the Earth's field within the field. And typically, the danger zone now is you absolutely have to keep the 5 Gauss line within the room. Okay. So half Gauss would be Earth's magnetic field. So that's not a problem. So you're allowed to have about 5 Gauss in areas that are outside the magnet room. So what that leads to is like when you're sighting a magnet, so this is a magnet that we were trying to sight, and it just so happened that the 5 Gauss line, whoops, poked a little bit beyond the back of the wall and given the position of the magnet. So if people were going through here, we had to make sure that we brought the 5 Gauss line within the wall. And so to do that, we actually had to move the magnet like 27 inches in the room, right? In addition, the other thing that helps is we have this big piece of of metal here, of iron, sort of to sort of reduce the magnetic field as well. So that's called shielding. Okay. So we've talked about sort of magnets where the person goes in like that, but there are other types of magnets that are sort of like donut designs where you can either stand in the magnet or you can lay flat. And so these are tend to be very helpful for like if you want to study people standing or bending and things like that, or if someone's very claustrophobic, okay, then these open designs can be used. The other thing that's going on with magnets is there is a helium shortage in the world. I think 5 years ago or so, probably pre-COVID, you couldn't even get the helium balloons for party balloons because there wasn't enough helium. So helium is something that is most of the helium is generated at sort of nuclear plants, nuclear facilities, and so the supply of that depends on sort of how well the government runs. And so when the government's not running well or decisions are made, there can be helium shortages. So that's led the manufacturers to sort of go to sort of lower helium designs. And so that's one of the changes in the field where instead of needing on this side, you have 1,500 liters of liquid helium, this magnet only uses 7 liters of liquid helium. And so this is just based on designs where they're able to do much better refrigeration just by conducting the heat away from the magnet. Okay. For example, this is another one that doesn't use very much helium. I think this only used, how much does it say? It doesn't really say, but and this also makes, oh, this is for a neonate. So this is a very small helium design. And so the nice thing about not needing, and so this is cryogen free, which means it doesn't even need helium. And so that just, anytime you don't need helium, it just makes it much easier to site your magnet, right? Because if you need helium, you have to provide an outlet for the helium, okay? Because the other way you can die in an MRI room is if, let's say we're in this room and for whatever reason, it started quenching, so it started giving off helium. Okay. So this room will start filling up with helium, right? So in that case, what should you do? How should you get out of this room before you die? So you have this thing that's giving off helium. So this helium, now helium, if you breathe helium, it's not going to help you, right? So helium is lighter than oxygen, right? So if I sit here, I'm going to suffocate at some point. So what should I do to get out of this room before I suffocate? Yeah, go to the floor, crawl out. Okay, because all the oxygen is going to be at the bottom. All right. So people unfortunately have died because of that, especially people installing MRI systems where they just weren't even aware there was a helium leak, and all of a sudden they just suffocate and they fall off a ladder or something like that, and they die. Okay. So I'm just giving you all the dangerous parts today, so you have respect for the system. All right. Luckily, this system here would be fine because there's no helium, right? So you just have to worry about things flying into the magnet. This is a very cute magnet for like neonates, so designing a smaller magnet, and that makes the design a little easier because uh, there's not as much wire to create the field for such a small area, and it's easier to take the heat out. Okay. And so this is just an example. And the other thing you can do is people are going from low temperature superconducting wires to high temperature superconducting wires. So then you need even less helium. And so that really helps you reduce the size of the magnet and also the weight of the magnet. Okay. So those are things that are really important. And then there is even these sort of portable magnets. So this is something from a company called Hyperfine, which is the magnet is shown here. It's a very low field magnet, 64 millitesla, so very low field strength. And the idea is and we'll talk about this later, with deep learning and AI, they can get away with that field strength and get reasonable looking images. Okay. So the other thing that's happened is that we'll talk about in this course, we'll talk about how traditionally most MRI scanning and reconstruction has been Fourier based. Okay. And it's only in the last 10 years that with the improvements in deep learning and AI that people have been able to go away from the Fourier based stuff and collect much less data and create reasonably good looking images. And so we'll get into that a little bit because that is sort of the state of the art for medical imaging now. The nice thing about this one is this is something that you can wheel in You could buy one for your apartment, and wheel it in and keep it there. This is a picture of me in the magnet, okay? And this is one of my former postdocs looking at my images on their iPad. So this is really sort of very convenient and portable, okay? So this is something where, for example, people are trying to see if it might be useful for the ICU. You could just wheel it into the ICU, or there's even people who are saying, well, you could have like a truck that just goes around and you could have portable MRIs. And the other big thing that believe the Gates Foundation bought a bunch of these and have shipped them to Africa. And so providing MRI for areas where you don't really have the infrastructure or the money to support one of these big MRI machines. Because those big MRI machines, they need a lot of cooling, they need power. It's very infrastructure dependent. Okay, so so we've talked about this part of the magnet. So all the wiring, the main field, the main field here. So now we're going to talk about the RF. And there's always going to be in most magnets what's called the body coil. So this is going to generate RF fields across the whole magnet area. And then there can also be sort of what we call localized coils. So this could be a coil that you could put just around the knee. And then you could also have coils that are sort of along different body parts. So the T here means transmit and the R is receive. So you could have so this would be a transmit receive coil. This would be a transmit receive coil. And the R means these are receive only. Okay. So the job of the RF coil is if it's transmitting, it's sending energy into the body. Okay. And if it's also receiving, it's listening to the energy that's coming out of the body. And that's how we're getting information in and out of the body. So you can have a coil that both transmits and then receives. Okay. You could also have one coil do the transmit and another coil do the receive. And so we'll talk about both as we go through the course. So these coils are a lot sort of less costly in terms of, they're essentially the simplest coil. I mean, you could build one of these coils in an hour. You just take a loop of wire and add some electronics, hook it up to your MRI system, and everyone here could build one of these coils very easily, whereas it'd be very hard to build, one of these helium-cooled coils on your own. You could build much smaller ones on your own, of course, but so let's start getting into some terminology. The main field is what we call the B0 field. Okay, this is the one that's like, for example, 3 Tesla. Okay. So that is the very strong field, and we call that the B0 field. So anytime you see B0, that's the main field. The RF field is what we call B1, and that tends to be much smaller in amplitude, on the order of the Earth's magnetic field. So these are much smaller fields. Okay, so that's why you can just generate them with little wires and things. And so, for example, the simplest coil would be this loop coil here, where it's just a loop of wire, and it's going to generate B1 fields. Okay, just from Maxwell's equations. This here down here is a picture of a body coil. So this would be a coil that generates RF fields within the confines of that coil. And so those fields they're typically designed, and we'll get into this. You'll notice that these coils are typically designed to have the B1 field perpendicular to the B0 field. All right, and we'll get into why that's the case, but that's an important thing to remember, that typically your most effective B1 field is going to be when it's perpendicular to the B0 field. All right. So we've talked about how the main coil is like an RF transmit coil. So it could be transmit only or it could be transmit receive. And then what's happened over the last 20 years is there's been a real focus towards having lots and lots of these surface coils. So those coils are the receive only coils, and you can have these coils, and as you make them, as people have sort of advanced in the field, we've just gone from, it used to be when you had an MRI, there was just one coil. You had one coil, transmit and receive. Now, if you get an MRI done, most likely your scan will have the body coil is going to transmit, and you'll have lots and lots of these receiver coils that are picking up the energy, right? And we'll get into why that's the case as we move into the course. So these are some examples of receive-only coils, and you can sort of see that they're, just basically loops of wire. Okay. This is one where there's many, many loops of wires going on and covering the whole body. So this is becoming quite popular these days where if especially I was just watching something last night where especially like people who, like billionaires, they're sort of trying to sell like where you get whole body MRI scans, to sort of check if you have cancer and things like that. So there is this trend towards sort of selling these very high-end MRI scans to people. This is another example. So this is sort of interesting because this sort of shows you how MRI is is very different culture from CT. In CT, most of the innovation is done in industry still. Okay. In MRI, most of the innovation is done in academia. Okay, by people like you. Okay. So this is what you're seeing on the top here is a coil that was built by some grad students at Mass General Hospital at MIT, at Harvard. And so this was the prototype coil, and you can sort of see it's got little loops of coils here, okay? So each one of those loops is a little surface coil. And so once they prove the concept, so this has 32 of those coils arranged like in a soccer ball fashion. And then once that was proven, then Siemens took that concept and came up with the coil on the bottom, which is the coil. There's like thousands of these coils now. Okay. So a lot of things that you see in when you go and have an MRI system done, most of it was invented in academia and then went to industry. And part of that is the MRI companies, for whatever reason, early on, they just made the software open to people. So you basically you can write your own code, and so that allows a lot of innovation to happen. So essentially, they were sort of, in a small sense, open source before even open source was fashionable. Okay, they basically shared the IP so that other people could develop. Okay, and the last sort of coil we're going to talk about is the gradients. And so this is there's typically going to be three gradient coils. There's going to be X gradient coil, Y gradient coil, and Z gradient coil. And their job is to create changes in the field. Okay. And this is what lets you do imaging. Because essentially, if everything is uniform, then it's going to be hard to tell, is the signal coming from this part of the body or this part of the body? So to make an image, you need to make different parts of the body sort of act different from a magnetic point of view. All right. So that's what these gradient coils are doing. They're going to make it so that the field changes depending on position. And as the engineer, you tell it how to change the field. So you know what you've done. Okay. So we'll get into this a little later, but just to present it here, the total field that we talk about, and typically we're always going to talk about things in the Z direction. Okay. Z direction is essentially for the magnets like that, is sort of along the direction. Okay. So that's always going to be the Z direction for this course, at least. Okay. So that's the direction of the main magnetic field. So the Z direction we're always going to say is that's the B0 direction. Okay. So whatever B0 points in, that's the Z direction by definition. Okay. So that field, there's always going to be a B0 part of the field. So we're going to assume there's a uniform part of the field. And then on top of that, we're going to add what we call gradients in the field, because these are fields pointing in the Z direction, but they're going to change. So for example, it could change, it could get stronger or weaker as I go in the Z direction, or it could get stronger or weaker as I go in the X direction or the Y direction. All right, so that's what we mean by gradient. So for example, here, we have each of these arrows here is sort of indicating the strength of the field. And so in this case, as I move along in the Z direction, the fields are getting stronger. Okay, so in that case, we would say that's a GZ gradient, which is dBz dZ. That GZ gradient is greater than 0. Okay. Here, over here, what we're seeing is, and let's say this is the Y direction, we're seeing that the field's getting stronger. The Z component of the field is getting stronger as I move in the Y direction. So there we say GY, which is equal to the delta BZ over DY, that's also greater than 0. So that's all we mean by gradients. So today we're just sort of introducing that concept. And then the field at any point in space is determined by both, it's the sum of your uniform field and all your gradient fields. All right, and that's what we're going to find out allows us to do the MRI image. So these coils, the simplest way you could do a coil, a gradient coil, is you could have one coil with current going one way and another coil with current going the other way, and that would create a gradient. Okay. But that, although that's the simplest gradient, it's not very well, it's not linear, it's hard to control. So typically, there's going to be these very complicated patterns that are sort of computer generated. Okay. So for example, this is one pattern here. And the other thing about gradients is MRI is, has anyone been in an MRI machine? Okay. So what surprised you about being in the MRI machine? Anything? It's loud. It's really loud. It's warm. Okay. Yeah, that depends on how they've set the settings. You can there, I've been in very cold MRI machines. So if the room is very cold or they have the blower on, it can be very cold. Okay. So yeah, one of the main there's two main complaint patient concerns about MRI. One, sometimes it's very claustrophobic. People feel very claustrophobic. And second, it's very loud. Okay. So typically you're going to be given earplugs or earmuffs, or maybe like noise canceling headphones. Uh, why is it loud? As we're going to see before, what's happening is we're going to be turning these gradients on and off. Okay, so sometimes the gradient's on in the X, sometimes on in Y, sometimes in Z. So there's going to be these time varying gradients. Okay, and they're going to be switching. It just so happens that the frequency they're switching at tends to be the audio frequency. Okay, so you've got current running through these coils in the presence of a magnetic field. So the Lorentz force makes those wires vibrate. Okay. And so that's what you're hearing. You're hearing these, it's essentially you're in a big loudspeaker. Okay. And so for example, it's very common to have like a 1 megawatt gradient amplifier. So that means we're putting 1 megawatt of audio energy into that thing. Okay. Not all of it's going to get to the sound, but just sort of for comparison, if you went to, I'm not really sure where I got the stat, but the Metallica, does anyone who know who Metallica is? Like a heavy, rock band. Yeah. So it's a rock band. So for their 2017 world tour, they had 367,000 watts of energy for their system. So basically, you could bring an MRI system to like a stadium tour and just like have it play sounds. Okay. It's gonna be that loud. All right. The other thing that the gradient amplitudes we look at, we see here, they're about 5 Gauss per centimeter is like the maximum we might see. So that means that you're changing the magnetic field on the order of the Earth's magnetic field. So that's a change of half a Gauss of magnetic field in 1 millimeter. So that's what we're talking about. We're talking about small changes in the magnetic field, but they're very well controlled. But because we want to switch them on and off, it takes a lot of power to do that. Okay. Okay, and then the last thing with an MRI system is that there's a thing you see typically as a patient, the MRI, the bore. There's a lot of electronics on the side, especially with new designs, and there's a whole lot of other sort of things like computers and amplifiers and power supplies that are in the equipment room. Okay, so there'll typically be you have the MRI system, and you'll have wires running up through the ceiling and down into another room. Right, so that's what you see, and then typically as you'll see, the person is sitting outside the magnet and there's a wall there. So the whole room is covered in copper foil to avoid having radio frequencies get in. And we'll talk about why that's important. And then the person will be running the console behind that. Okay. So that's sort of, if anyone takes Bioengineering 278, you'll get an opportunity to go into the magnet room and actually do your own experiments. Okay. That'll be done on one of our magnets. All right. Okay, and the cool thing about MRI is with the same system, just by changing the software, you can get lots of different information. It's almost like, like how on an iPhone you have all these different apps, right? It's the same phone, but you have all these different apps. So basically, the apps on an MRI system are called pulse sequences. Okay, so every pulse sequence, which tells you how to play out these different pulses, so there's going to be RF pulses and gradient pulses, just by changing how you play those out, you can create different types of image contrast. So for example, here we're showing you just the same brain, but you can sort of see that it looks different. Okay. And these are just three different scans on the same person done at the same time. Um, sequentially, but we're trying to look at different things. So for example, uh, this part of the brain, the dark part of the brain, that's your ventricles. These are these cavities inside your head that have a lot of cerebral spinal fluid in it. So you can sort of see on the left, it looks dark, and on the right, it looks very bright. Okay, so how the image look depends a lot on how you've programmed it. And we'll get into a little bit of that later in the course. Here, we're looking at sort of iron in the blood. So you can sort of sensitize your sequence to look for iron. Here, we're just looking for where are the vessels. So this is like what's called an angiogram, where you basically just want a picture of the vessels. Here is where you want to actually measure the wiring in your brain. And so this is pretty incredible. This is only like 10 years old, this technology, in terms of I can take any of you and put you in a magnet, and in 8 minutes, I can get a wiring diagram of your brain. And this is the only way to do it, right? There's no other way to do this in a human being, right? Well, the way they do it in animals sometimes is they will inject a tracer into one nerve and watch it go to another place. But then to actually do the measurement, they actually have to kill the animal, right? They actually have to like cut it open and see where the tracer went. But that's only going to trace one nerve at a time, right? There's, billions of these wires in your brain. And so MRI is the only way. And we'll talk about how you do that with MRI towards the end of this sort of quarter. So you can see with 8 minutes, you get a pretty good map. If you're willing to stay in there for 25 minutes, you get even more information. Okay. So this is now sort of standard of care in terms of getting these sort of amazing sort of wiring diagrams of your brain. All right. And the other thing you can do, which is sort of my area of research, is I can also put you in the magnet and I can tell what your brain is doing. Okay, so this is the area called functional MRI, where I'm sort of seeing what's your brain doing? Like if you're doing a gambling task or you're thinking about your homework or lunch, how's your brain acting differently during those tasks? And we'll talk about how that works later in the course. So this is with the hardware is all the same. Okay, it's the same MRI system. I've just changed the app. Okay, so that's pretty cool. Okay, and then the other really cool thing about MRI, it's as things are getting, as electronics are becoming cheaper and more sort of powerful, is you can actually build these on your own. And so there's a lot of open source imaging, for example. You can go online there, you get a plan on how to build your own MRI system. There's plans for circuit designs and it'll tell you exactly how you want to build. If you want to build one for like your apartment or something, you could build it. Yeah. Yeah, you could just, if you just want to just have fun, you could just take a bunch of wires and make your own little magnetic field, or you could actually get a bunch of little like permanent magnets. We'll talk about that later in terms of, because as people are thinking about how can you get magnets out into like either rural areas or like, developing countries or even battlefield, you can't bring a big magnet. So yeah. Yeah. Yeah, no, you could do that. You can do that. Yeah. The images aren't that great. They're not going to be like if you have brain cancer, you're going to want to go to like the high end, you know, um, you know, one of the things we have here at UCSD, for example, right? And you're going to want to have the best radiologist in the world read it, right? But if you're in the middle of nowhere, right, and they just want to know, do you have like a brain bleed? You don't necessarily need the best system. You don't need the best radiologist. You just want to see, oh, is there some brain damage? And then this sort of like what they call triage, right? You're just trying to get an idea of do I need to fly this person out soon or are they okay? So you don't always need the best image depending on the circumstance. Yeah, good question. Okay. So now we're going to that's sort of our intro, sort of the overview. And now we're going to talk about what each part of the system does. Okay. And there's going to be four main concepts that we're going to cover. Um, and just sort of as a preview that starting now, basically, before the next lecture, there's going to be on Canvas will be posted like a pre-lecture quiz. So basically, it'll be typically like four questions that if you're even like half awake during the lecture, you should be able to answer the questions, right? Um, and uh, and so there'll be an announcement about that. So that'll be part of the participation grade. So just it'll be announced and you'll sort of sort of see what that is. So we'll send an announcement out. And I'll typically post those like right after the lecture. So you could just do it after the lecture. You don't have to wait till the next lecture, but they'll be due like 10 a.m. of the day of the next lecture. Okay. So just so everyone is aware if that's what's going to happen, just to help you consolidate some of the concepts. So the four main things that you need to know for MRI is one, the main magnet does something called polarization. So we'll talk about it today. The RF coil does something called excitation. And the gradient coils do what's called encoding. And then the RF coil also does reception and integration. Okay. And we need all those four steps to get the MRI image to work. All right. So today we'll talk about polarization and excitation. All right. So we need to sort of give you some really basic concepts about what we're trying to do with MRI. Okay. So has everyone here heard of spin? Or I mean, now with like quantum computing and everything, it's even more sort of in the popular press. But spin is essentially the intrinsic angular momentum of elementary particles, electrons, protons, neutrons. In this course for MRI, we'll be talking about the spin of protons. Okay. And spin is a very fundamental concept in quantum mechanics, but we're not going to do any quantum mechanics in this course. We're just going to give you some very basic ways to think about spin, right? So the most important thing, one of the most important things for this course is that um, the protons have both, that with spin, have both angular momentum, so it's intrinsic angular momentum, and they also have a magnetic moment associated with it. Okay. One way to think about that is if I had a ball of charge and I spin it around its own axis, right? That ball certainly has angular momentum, right? Because it's spinning around its own axis. But you can think about it, the charges are also moving around like this, right? And so this is a current, right? So if I have a current, I'm also going to have a magnetic moment, right? So that's the thing to realize. And so basically, sort of a way to think about it is, it's a very rough classical analogy. Um, and so that means that, and typically what we're going to say is the angular momentum is defined by something called S. There's gamma, which we'll see later, is a gyromagnetic ratio, and that relates the angular momentum to the magnetic moment. All right. So for example, in this case, in this course, we're mostly going to be dealing with the hydrogen proton. Okay. And this has spin 1/2. So we're going to be dealing with spin 1/2 particles. All right. Now, there are other things like carbon-13, fluorine, sodium, phosphorus, which you can also do MRI imaging with, but it's much less common. So typically, if you go to the hospital, they'll be doing imaging of your of the hydrogen proton. If it's a very researchy place or the special exam, they might be looking at sodium or potassium or something like that, but that's pretty rare. Okay. Okay, so let's revisit the momentum, the magnetic moment. So here we're showing if you have a loop of wire with area A and a current I, the magnetic moment would just be the current times the area, and n hat is just saying which way that magnetic moment is pointing. Okay. So one of the more important concepts is what happens if I have a magnetic moment, a little magnet in presence of another magnet. Okay. So has anyone here actually held a physical compass in their hands? Does anyone know what a compass is? Okay. So some of you know what a compass is, right? It's sort of like, it has a needle that points north, right? Okay. Um, so I mean now you could do it with your iPhone, but it used to be like in the old days you could take a needle and magnetize it and put it through a cork and put it in water and it would point north. Okay. So what the point is that if I have a compass needle, when it points north, that's its lowest energy state, right? If I turn that compass needle away and point it south, that's its highest energy state. And it's going to want to go back to its lowest energy state once I let go, all right? So just remember that the lowest energy state of a magnetic moment is always going to be when it's aligned with the main field, and the highest energy state is when it's anti-aligned, all right? So just think of the compass needle. So this is the compass needle example. And now the other important thing to think about is, and I think some of you, or most of you probably heard the Boltzmann distribution, right? So basically, if things can be either in this energy state, so it's like lowest energy state or highest energy state, or it could be at some intermediate energy state. So the Boltzmann distribution just tells you what's going to be the probability of finding something in those different states. Okay. So just intuitively, you expect most highest probability to be in the lowest energy state, right? Less probability as I get higher energy, and the lowest probability is when I'm in the highest energy state. So that exponential decay of probabilities is your Boltzmann distribution. Okay. Uh, the best analogy I've heard about this is sort of thinking about like if you have like a parking structure where there's no like, A, B, or student parking, you can park anywhere you want. Essentially, if you look at the occupancy of the floors, typically if you go into a parking structure, if you can, you're going to park on the lowest floor, right? If you've had a lot of coffee or you're just really excited for some reason, you might just decide, I just want to drive to the top floor, right? But in general, you're not going to do that unless you feel like there's some reason. So if you look at the occupancy of a parking garage, it will roughly follow a Boltzmann distribution. Okay. Okay. So here's the picture. Here, in the presence of when there's no magnetic field, internal magnetic field, then there's no preferential direction for the magnetic moment, it's a point. So any direction is fine, right? So if I think of summing up a bunch of vectors in random directions, what's that going to sum up to? Zero, right? Because for every one pointing this way, I've got one pointing that way, and the sum of those two vectors is zero. Okay. Now I put in the magnetic moments in the presence of this magnetic field. And now there's going to be higher probability that they're going to be pointing this way, and then it's going to exponentially decay anti-aligned. So when I sum up all those little magnetic moments, I'm going to have a net sum that's aligned with the magnetic field. Okay, and that's what we're going to call our M sub naught, or equilibrium magnetization. Okay, so even right now, sitting in the Earth's magnetic field here, I don't know which direction it's pointing, but your spins every one of you has a slight magnetic moment, net magnetic moment pointing in the direction of the Earth's magnetic field. Okay. And in fact, you can actually use that. You could actually do Earth field MRI. You don't even need an additional magnet. If you have sensitive enough sensors, you could actually create an MRI system with just using the Earth's magnetic field. Yes, question.
But your cells care if like I'm facing this way to the magnetic field or not.
Yeah, that's a great question. So that sort of gets the safety of MRI. As far as we know, um, just being in a high magnetic field, at least the ones that are most commonly used, no one has determined any long-term effects of that. So it seems like, because it's not just, I mean, it's every proton in your body is being affected, right? In a probabilistic fashion. So there are issues with now, the only issue that comes when the higher magnetic field is like, if you go to like a 7 Tesla magnet or a 10 Tesla magnet, you can get nauseous or dizzy. And that's because as you're moving, typically, like if I just shake my head in a magnetic field, I'm creating currents in my head, right? So like I was once working on at the back of a magnet, I just sort of started feeling really weird because as I was moving my head near the magnet, I was causing currents in my brain. And that was doing something, I don't know what part of my brain it was affecting, but it was affecting my brain. The other part that can happen is you can have, as you're putting RF energy in, you can cause burns. And so we have to regulate that. But for your question, at least the fields that have been used now, there doesn't seem to be an effect. And even these higher field strengths, I mean, people don't seem to see any effects. And that's, MRI has been around for, let's see, 30, 50 plus years. Okay. And a lot of the people working in the field, like I've been in an MRI system like probably hundreds of times, right? So it's unlike X-ray, where when X-rays came out, the people who were doing X-rays on themselves all started dying, right? And MRI, I mean, they're the typical weird scientists. But we can't, I don't think you could, they're not any weird, like an MRI scientist is not any more nerdy than a CT scientist or, ultrasound scientist, as far as I can tell. Okay. So I don't, as far as we can tell, there's no long-term effects. Okay. Good question. Okay. So basically M naught is going to be made up of sort of all the sort of spins you have times sort of the average sort of magnetic moment. Okay. And it turns out that that is going to be proportional to your B field. Okay. So what that means is the bigger field you have, the more magnetic moment, net magnetic moment you have to deal with. And that's essentially your signal. And that's the primary reason why people keep building these bigger magnets, because they're trying to get more signal. Okay. And this is just showing on the bottom as a function of field strength. This is your signal noise ratio, and it sort of goes up, somewhat parabolically, almost linear at some point. Okay. Okay. The next thing we need to talk about, which is a very important concept, is what happens to a magnetic moment um, with angular momentum in the presence of a magnetic field. So if I have a magnetic field pointing this way and I just have a compass needle, it's going to want to align this way. And that's all, right? And if I perturb it away, it's just going to try to go back. Okay. But that's because this has no angular momentum, right? So now we want to ask the question, what if this spin is spinning around its own axis? What's going to happen then? Okay. And that's where I always bring this prop with me. So some of you may have seen this in a physics course before, but do it again because it's always fun to do this one. So this is going to represent my spin, okay? And the idea is that this is obviously the lowest energy state for this thing, right? And the highest energy state would be if I went this way, right? And this would be an intermediate energy state, right? So if there's no angular momentum, then it just goes back to its lowest energy state, right? Okay. So now I'm going to put it into sort of an intermediate energy state, right? And I'm just going to spin it. Okay. And now it's precessing. Okay. So this is sort of fundamental to MRI, that the spins are going to precess around the main field, right? So that's essentially the concept you need to have in mind. Okay. So we said if it's non-spinning, then it just aligns. If it is spinning, then we can go through these equations and it's going to follow the magnetic moment is going to follow this equation of motion, which let's look at what that means. So that means it says d mu dt, which is the change in mu with respect to time, is equal to mu cross product with gamma b. Okay. So I have b this way, right? And I have mu pointing this way, let's say. Okay. So the cross product, right, is going to be pointing this way, perpendicular to this. So it's going to be perpendicular to this. And so it's sort of, we're going to just make a move this way. But at every point, that cross product is going to change. And so it's going to just make it go in a circle. Okay. So that's all that's saying, that the our spins, so not only are your spins somewhat aligned with the Earth's magnetic field right now, but they're precessing around the Earth's magnetic field. Okay. And then your homework, you'll figure out what frequency they're precessing at. Okay. So right now, even in not an MRI system, you're already in a magnetic field. And so you are exhibiting some of that precession. So the frequency at which they precess is what's called the Larmor frequency. Okay. And so Larmor frequency is given by omega equals gamma, gyro magnetic ratio, times B, the magnetic field. So whatever the field is at that point in space, you multiply by gamma and you get your frequency. Okay. So for example, in the Earth's field, you take half a Gauss, multiply by gamma, and you figure out your frequency, right? And so we already went over Tesla and Gauss. So just so you know what gamma is this is for hydrogen proton. Whoops. This is for hydrogen proton. It's about 26,000 or 27,000 radians per second per Gauss. Or what I like to think about is units of, so I sort of have this to memory, like 4,258 hertz per Gauss. Okay. So if I had if I was in a 1 Gauss field, the spins would precess at about 4,000 Gauss. All right. And then different nuclei have different magnetic moments and different gyro-magnetic ratios. So this is the one for hydrogen proton we just went over. The other thing that makes hydrogen proton sort of the most prevalent way of doing MR imaging is obviously you have a lot more hydrogen, the abundance of hydrogen, much more than you have of other things like sodium. Okay. So you got a lot of spins there. So there's a lot of signal to work with. And so that's what, for most clinical exams, you're going to do something that with hydrogen proton. Okay, so let's talk a little about the Larmor frequency some more. So omega is in radians per second, but it's also useful to think about cycles per second or hertz. Okay, so that would just be omega divided by 2 pi. All right. So for a 1.5 T system, the Larmor frequency is going to be about 65 megahertz. Okay. For comparison, sort of one of the lowest frequencies, at least in San Diego, for FM dial is about 89.5 megahertz. That's kpbs, right? So you're just below the FM range. And then if you go to like a 3 Tesla system, which is shown here, you're at 127 megahertz, and that's in the civil aviation range. Okay. Yeah. What am I doing? What? We're looking at the Larmor frequency. Yeah. So basically, essentially, the rate of precession of the spins. Yeah. So that's the Larmor frequency. Yeah. No, for proton. Yeah, that's right. This is for proton. Yeah, so this would be like you could take, yeah, you just put that number in. And then this is a really good website to go to if you have any questions. It's called MRIQuestions.com. It's by a retired radiologist. It's a really good source. I mean, now there's ChatGPT too, so you can just go to ChatGPT. But before there was ChatGPT, this was probably your best source of general knowledge. Okay. Just beware, ChatGPT does hallucinate, and so you're allowed to use it, but you just need to be careful. Okay. Um, okay. So anyways, because it's in these frequencies that are used by a lot, like by airplanes or by radio stations, that's why we have to enclose the magnet in this copper shielded room. So this interference, this energy. So when we're doing the experiment, we're only listening to the energy coming from the sample, not from extraneous sources. Okay. Okay, and then the final concept I think for this one is that um, we typically, we might look at things that are, say, a 1 millimeter by 1 millimeter, 1 millimeter cube, or maybe a 3 millimeter cube. So we're looking at lots and lots of protons at the same time in any given voxel that we're looking at. Okay. So therefore, we're always going to take the sum of all those magnetic moments. Okay. And we'll get into why that's important as we move on in the course. But because everything is linear, the whatever that sum is also follows the same equation in motion. Okay. So it also precesses. So whatever magnetization we have is going to precess. Okay. Okay. So are there any questions about polarization? So polarization, once again, is just this concept of creating that magnetization. Okay. And then that magnetization is going to precess. Right. Okay. So we'll spend the last, I guess, is that right? Yeah. Okay. Spend the last 15 minutes talking about RF excitation. So the idea is that we said that the equilibrium state, if this is the main magnetic field, there's going to be some component of magnetization that's aligned, right? But it turns out to make images, what we need to do is we need to tip this magnetization away from its state so that it can precess, right? This is precessing, but it's sort of, we can't really tell, like you can't like, just as an analogy, it's hard to tell that this is spinning around its axis, right? And so if I just look at the changing magnetic field here, there's no changing magnetic field of this spinning around its own axis, right? So I have a receiver here to create a changing magnetic field. I got to make this tip so that now this magnet is moving around like this. So therefore, it's going to create a changing magnetic field. Does everyone see how why that makes sense? Okay. So that's the process of RF excitation. So the concept is that we want to tip this away or flip it away. Okay. And the angle we flip it is called the flip angle or the tip angle. Okay. You'll see both terms. So the most common flip angle is 90 degrees. Okay, so we'll sort of stick with that. But there's lots of different flip angles, like 5, 30, 45, 90, 180 we'll talk about later. Okay. But for now, we're going to mostly focus on, and what's shown here is in the diagram going from a 0 flip to 90-degree flip angle. And so at this point, this is going to process around like this, and we're going to listen to this changing magnetic field with a coil. All right. Okay, so this is sort of the picture of what's going on. So you still have sort of moments pointing in all directions, but the net moment, there's a net moment. And so that net, everything is processing around the field, right? And then we add some RF excitation to get it to move away from that equilibrium state. And this is sort of the process of excitation. We're causing these spins to go into a different state. Okay. So these spins really want to process around the B0 field, right? Somehow we're trying to get them to go away from that field. Okay. I mean, they really want to be aligned with this field. This is low energy state. And this is a very strong field. And we want to come along with a smaller field to get it to move away from that state. Okay. So the question is, how do you do that? So that's the idea. So we're trying to, and then typically, so you're seeing here, we've got the B0 field. Oops. A very strong B0 field here, and we have a much smaller B1 field that's perpendicular to that. And we want to use that much smaller field to somehow move it away from its preferred state, which is along this B0 field. Right? So it's similar to what would happen if, like, and I don't know where this is, but this person has like a car on a swing, right? And so imagine you went to visit your friend who had this, and you tried to get this thing to start moving. Okay. So how should you, and the only constraint is you're only allowed to use your index finger. Okay. So, and I would like you to get this moving so it's moving at least 1 foot in either direction. Okay. So what's what's the only way you're going to do this without breaking your finger? Yeah. So you have to hit it at the resonant frequency, right? Because if you hit it the wrong time, you're going to break your finger, right? Okay. So that's the idea. You have a very weak field. Like this is a lot of weight, right? That's the weight of this car is saying that this is a very strong force going this way. And you're trying to oppose that force with something that's very weak. So the only chance you have is to hit it at the resonant frequency. And each time you get it, you perturb it a little bit. That's what the B1 field is doing. And similar to a merry-go-round, okay? So imagine you had your friend standing on the merry-go-round. So they're going around, right? And I give you a little piece of thread that you can tie to them. And then I tell you your job, and it's like a 3 foot piece of thread, but if you pull it with more than a pound of force, it's going to break. Okay. So your job is to pull your friend off that merry-go-round. Okay. So how are you going to pull your friend off that merry-go-round with this thread? So the merry-go-round is going around like this, right? So what should you do to pull your friend off the merry-go-round? Go ahead. You got to run with them, right? And you're running with them, applying a very up to 1 pound of force, and eventually you'll be able to pull them off. So that's essentially what the B1 field is doing. It's going around with the spins are processing. So every time you're just getting it to move, and then you have to go along with the field to get it to come down. Okay. So the merry-go-round picture is very much analogous to what the B1 field is doing, because the B1 field's got to go around and essentially pull that spin down to where it wants to go. Okay. So this is an example here where the red is going to represent your magnetic moment or spin, and the blue is going to represent your B1 field. And it's going to go at the right frequency, the precession frequency. And you'll notice here, if you're at the right frequency, you sort of get that. So this is sort of like analogous to pulling that person down off of the merry-go-round, right? Okay. Now let's just say you're just a bit off. You're running a little too fast or too slow. You're running faster than merry-go-round or slower than merry-go-round. Then what's going to happen is you're just not going to be as effective, right? Your pulls are not timed correctly. Okay. And so in that case, the magnetization stays sort of where it wants to be. Okay. So the key is with RF excitation, we want to apply our B1 field at the right frequency. Okay. Um, the other sort of probably the last big concept we're going to put in today is um, even though the spins are moving around, at this, for example, in a 3 Tesla field, they're going at 127 million cycles per second. You don't necessarily, that's sort of complicated. That's sort of the laboratory frame of reference, right? But it's much simpler if we can consider what's called the rotating frame of reference, right? So essentially, the rotating reference is we're going to imagine we're in the same frame of reference as the spin. So we're going to move around with the spin. So it's essentially analogous to your friends on the merry-go-round and you see them spinning. Once you get onto the merry-go-round, you're in the same frame of reference. So in that frame of reference, if they were falling off the merry-go-round, in the laboratory frame of reference, they're falling off like this, right? But if you're standing right next to them, they'd just be falling like this, right? They're just going like that. Like you just see them falling off. You're not worried about this frame of reference. So that's essentially for this course, we're going to be in the rotating frame of reference, right? So the laboratory frame of reference is pretty complicated. You're thinking about this spin spiraling down, right? But if you're in the rotating frame of reference, it's just going like this, just like your friend is going off the merry-go-round. Okay. And so this is showing you what that looks like. So this is the rotating frame of reference. Okay. So that's a much easier picture to think about. We're just tipping the spin like that. Okay. Otherwise we can spend a lot of time tracking this, which we don't really care about too much. Okay. Now, if you had a very, very advanced sort of MRI, then you do sort of have to think about this. But for this course, we're just going to assume this. Okay. Okay, so the last thing I think we'll do is we'll end with a sort of a simple exercise on the flip angle. So um, the idea behind the flip angle is that the angle we want, say theta, let's say we want theta, let's say pi over 2 is a very common choice, like a 90-degree flip angle, right? Pi over 2 flip angle. So the way we get that is, remember, spins always precess around the magnetic field, right? If I'm in the rotating frame of reference, then it seems like there's no B0 field, right? Because there's no rotation anymore, right? So the only field that's there is the B1 field in the rotating frame of reference. So think about it this way. If I spin here, it's going to precess around this field, okay? And so it's going to precess at a frequency omega 1. And if I integrate that, that's telling me the rate of change of the angle. And if I integrate that over time, it tells me the total angle. So the first calculation, which I think there'll be sort of, when the next homework comes out, there'll be a very simple example of this, which is, what's the flip angle, all right? Or maybe on a pre-lecture quiz, I'm not sure. So let's do an example. So we'll do our first sort of MRI pulse. So for example, here, I might say, as a function of time, I want to apply a pulse that's going to last 400 microseconds. Okay. So I turn on a pulse and it has some amplitude B1. Okay. And what I want is theta to equal pi over 2. Okay. So simply, I just want to say, well, pi over 2 is going to be equal to the area of this, which is going to be B1 times the time I have it played out for, right? Times gamma. Right? That's essentially my integral, right? Okay. So then I can say that, well, I can just solve for B1 then. So then B1 equals pi over 2. Okay. Divide by 400 times 10 to the minus 6. Divide by gamma. Okay. And so this is my gamma here in radians, 2 pi times 4,257 hertz per Gauss. And this is my time. And it turns out if I play out a 400 microsecond pulse, I need to play out a B1 that's about 0.15 Gauss. Okay, about a third the Earth's magnetic field. So these are fairly tiny magnetic fields we're playing out. All right. Okay, so let's end with sort of a question here. And the way we'll do the question is, uh, I guess I could set up a poll online, but we'll just sort of have people shout out what they think is the right answer. So for this one, we have a few minutes left. So here's a question. You have an RF pulse of the form A times sync T over T. Now, Professor McVeigh went over the sync function with you guys, right? Okay. So that means the zero of this sync function is at T, right? That's what the sync function looks like. So it's got an amplitude of A, and T is equal to 250 times 10 to the minus 6 seconds. So how do we pick a flip angle? Select an amplitude A, give a flip angle of 45 degrees or pi over 4. Okay. And for this case, you can assume that gamma over 2 pi equals 4,000 hertz for Gauss, just to keep things simple. Okay. So your job is to just pick the closest answer of how large should A be? Okay. So go ahead and in the next 3 or 4 minutes, go ahead and you can discuss this with your neighbor. And let's see what you get in terms of how big that A should be. And I'll open up a poll online if people want to respond online. Okay, in the last 2 minutes, let's go over this together. So first of all, we know we need to get the integral of this, right? So any ideas on how do we do the integral of the sync function? Anybody want to do that? Okay, probably not, right? That's going to be very sort of tedious. So what we want to do is we're going to give an example of essentially, does anyone remember if I have sync of t, what is its Fourier transform? Rect, right? Let's just go to the rect function, right? Rect of f, right? And I have sync of t over tau by the scaling theorem that goes to t times rect of ft, right? Okay. Now, the area, we know that the area of a function is just equal to its Fourier transform at 0. Okay. So the area is when f equals 0. So then the area is just going to be a times t. All right. So if I have the area, so I know that a times t times gamma, I want that to equal to pi over 4. Because remember, the flip angle is equal to gamma times b1, the integral of that. Yeah. So sort of this is sort of that integral of b1, right? And then the flip angle is equal to gamma times the integral of b1. Okay. So I forget what the answer is for this. We'll pick it up next time. So that's just sort of an example of things that go on all the time. And so the cool thing about this is that the sync function is not picked randomly. right now, if you go to almost any MRI system in the world, it's playing out these sync functions or some example of sync functions. So these sync functions are prevalent. So essentially, if you go down into the depths of any MRI code, it's doing calculations exactly like this. Okay, so what you're going to learn in this course is essentially the calculations that are actually done in practice. And if you actually put a scope onto an MRI system and look at the RF, you'll see sync functions. Okay, so before I started doing MRI, I just thought sync functions were just sort of some sort of abstract quantity. Now it's sort of, you know, I know that they're used everywhere, every day. Yeah.
It plays the, what's the y-axis?
The amplitude of the B field. Okay. Yeah. So this is time, and this is B1. So if you looked at, so this is the coil. Like if you looked at the field coming out of the coil, there's some current that's going into that, right? Or and there's an RF amplifier that's generating that voltage and current. So that's programmed to generate something like a sync function. All right. Okay, I think that's good for today. So we'll call it there. If there's any questions, feel free to come and ask up here. Otherwise, we'll see you Monday, right? Okay. All right.